Well, it seems to work in the laboratory and in real factories too. Vision systems depend on having a relatively easy feature to search for, a bit like that white ping pong ball against black. Here, Fref reports from America on one advanced industrial application.
Two men install a car windscreen. Almost without thinking about it, they're communicating, taking cues from each other and from the production line as it stops and starts. They're governed by the speed of the line, which gives them only a small window of opportunity to press home the glass. They do this with human skills which we take totally for granted. Recently, at the General Motors Buick City plant near Detroit, they've automated this skilled but tedious part of the car production process. Here, instead of men, robots cooperate with each other in what's known as a flexible work cell. On the left, a group of 4 robots prepare windscreens for a range of cars of different shapes, sizes, and colors. On the right, a vision system looks at each car as it comes along the production line and tells one of the robots exactly where to place the windscreen, a slightly different position for every car. And round the back, a similar group of machines puts in the rear windows. But the system isn't yet smart enough to load the right windscreens in the right order for the cars as they arrive. A carousel still needs a man to load it. This takes the windscreen to 3 robots in turn, which prepare its edge with the chemicals which will glue it to the car. If the glass weren't held firmly in the right position, these robots wouldn't have any idea where it was. They're blind. But no human would spray so evenly, or so quickly, or so tirelessly throughout the day. Each robot has its own computerized control system to guide its complex movements in space, and a different program for each size of windscreen. So how do the men and the machines know in what order cars are coming along the production line?
Every car on the assembly line has one of these attached beneath it. It's a short-range microwave transmitter programmed with a numeric code which identifies what kind of car it's supposed to be when it comes out the other end of the plant. This one might say, "Hi, I'd like to be a red Buick LeSabre 2-door with black seats, a thermal rear window, and the following options." As a car moves down the assembly line, receivers in the floor pick up this number, and the men and the machines in each workstation act accordingly.
A massive cabling carries messages between the machines. It tells them when to start or stop, which program to run, and brings the latest news from the various sensors. Software was developed here specially for this work cell. The most difficult thing was tying in the vision system. That's the unique feature. Using a number of black and white cameras, each car is viewed from a number of angles under very bright and very even illumination.
The vision has to be within 3 to 4 millimeters accuracy when they load the windshield in the car. It's looking for the contrast and the edge around the windshield opening. It focuses in on that point, and there are 4 different cameras that look at that point, giving us a 3-dimensional picture of the car edge.
What you're seeing here in real time are the lines of high contrast that the computer has picked out from each black and white image. From this massive information, it has to identify the edges and angle of the window opening in each view, then use a bit of 3-dimensional trigonometry to tell the robot precisely where to move.
Now, with the ping pong ball, Mike, you're looking for a single point in space. That looks to me to be much more complex, is it?
Not particularly. After all, General Motors went to a great deal of effort to simplify the contrast colour of the car, the lighting. They had 2 or 3 cameras sprinkled about. They were looking for a very simple feature. And again, to triangulate, to find that windscreen opening in space, much like the ping pong ball. In both cases, they needed vast amounts of computing.
Right. Let's move back to our problem here with the block amidst all the clutter. Here is a remarkable piece of film which shows a computer solving that problem.
Well, here you can see an example of a bin full of castings with one stray object which has to be removed because the computer only knows about one kind of object. Central to the operation of the program is that the computer has a model inside its memory of that casting. In this case, it looks like a computer-aided design model. The robot uses a laser ranging system to compute explicit depths, so solving the tough vision problem we saw earlier. Here the edges are depth edges where the surface intersections on the objects.
It's only got the one eye. Has it?
It's only got the one eye, but it's computing depth. Now what it's doing is finding little edges and trying to match them up against its model that's stored in its memory. And every time it finds one, it makes a hunch about where a model is in the memory of the computer.
So then it tests that hunch against other things. It predicts that there must be another edge over there and then tries to fill it in.
That's right.
Works.
And the more information it finds, the more it can narrow its hunch until eventually it fills in an entire object, like the one you've seen here. And of course, once it's filled in an object, it'll go and verify as far as possible what it can see. Here you can see it testing edges, filling in models, then going around finding another edge that looks particularly as though it would support a hunch, and then filling in another model and so forth until it's found and accounted for all of the objects that seem to be in this particular bin.
But it can only deal with those particular objects.
It can only deal with those particular objects. You'd have to teach it a new object for a new bin.
That looks to be very sophisticated. Is that state of the art?
That's pretty much state of the art in industrial vision these days, yes.
Right. Thank you, Mike. We'll come back to you later.
Well, the main economic reason for using robots is to be able to make automated industrial processes more flexible. That means being able to change what you make without having to change all your machinery and start all over again. One of the frustrating problems in industry is the long time it often takes between designing something and getting it into production. For example, this is the old way that biscuit molds used to be made. An enlarged drawing of a biscuit is stuck on the surface of a block of brass and carefully cut out by a skilled craftsman. He then follows the contours of this giant mold using a device something like a child's pantograph. Through a series of mechanical links, this reduces everything down to the size of the final biscuit mold. 100 of these need to be cut out to make one biscuit roller, and that used to take as long as 3 months. By designing the biscuit on computer-aided design equipment, the whole process can be speeded up. The designer defines the exact dimensions of the mold on the screen. The system then sends the instructions for the way the mold is to be made directly to a computer-controlled robotic milling machine. The biscuit molds can be cut directly on the roller, a row at a time. All this has cut the time taken to make a roller, and therefore the time to make a new biscuit, from 3 months to as little as 3 weeks, giving this company a cutting edge over its competitors. If new products can be designed quickly, flexible equipment is needed to make them. This robot machining centre can do a range of different jobs. Here it's finishing off a plastic moulding, which is part of a switch housing. It can grind and drill in a variety of ways which are determined by the robot's program. If the design of the part alters, all you need to do is to alter the software. If designs can be changed easily, and the machines are capable of making a range of different things, the next thing is to be able to move materials about the factory in a flexible way. That means programmable conveyor systems like this one, able to move any parts to any machine. This factory can make many different parts, and make just a few of them as quickly and as cheaply as making a large number. To educate engineers about the design of advanced manufacturing setups, models like this are being used to build and test prototypes, making it quicker to get the real thing into action. This one, built out of parts you can buy in any model shop, was actually used to design part of a Volkswagen car plant. The control software was developed on this, and all the bugs ironed out before the real thing was built. Well, people have been predicting the renaissance of industry using advanced manufacturing techniques like these for some years now, but it hasn't quite happened yet. One of the things which has held things up has been incompatibility, the inability of one computerized machine to communicate with another, as Freff found out back in that General Motors factory.
If you look below the surface of the automation in this General Motors car plant, there are clues that this is still far from the promised land of integrated, flexible manufacturing. Bits of paper with special instructions still accompany each car. Paper still duplicates the information sent out by the transmitter fitted underneath each body, because the transmitter only gives information to some parts of the production line and not to others. And other information appears on screens to be read by the men on the line. And in the central computer room, an island of quiet in the middle of the shop floor, various incompatible computer systems look after different parts of the car-making process, tracking orders, scheduling the work, controlling the conveyor systems, and so on. We found Prime computers, IBM and DEC systems, and Tandem terminals sitting side by side, unable to exchange data with one another. Almost all the computer-controlled machines in the plant have to be programmed and reprogrammed locally. They aren't yet linked to a central computer, or to each other.
GM has over 40,000 intelligent devices in its various plants. Automatic loaders, code readers, robots, vision systems, and more. The difficulty is that very few of these devices actually talk to one another, fewer than 15%, because they're made by different manufacturers in different countries, and their hardware and software is typically incompatible with everything around them. GM feels that this lack of standards is holding up the development of computer-integrated manufacturing, so it's flexing its industrial muscle and forcing equipment suppliers to conform to a new standard called MAP, the Manufacturing Automated Protocol.
MAP is not a programming language. It's a way of passing data between machines of different makes, and it should make it easier for machines like these to be programmed remotely with information sent from a central computer or even directly from computer-aided design equipment. By making such links possible, GM hopes to cut the time taken between design and manufacture by as much as 50%. MAP could replace all of today's special cabling and interfacing with a single coaxial cable to connect all the machines together. The aim is tighter control of the entire production process.